Good day, everyone. This is Professor Friday coming at you one more time. I'm going to try something new today because I lost one of the apparatuses that I used to do the overhead videos, so we're going to try something new. So, plan for today is we're going to evaluate the definite integral from x equals 2 to x equals 4 of x plus 2 over x squared plus 3x minus 4. The idea behind this problem is that we are going to perform the algebraic operation of the partial fraction decomposition. Now, there is something noteworthy that we're going to want to try right away, which is to note that with any rational function, we do potentially have a domain issue. So, first thing I'd like to do is actually check to make sure that the entirety of the interval that we use here is contained within the domain of the rational function. Now, we know that when it comes to denominators, we are not allowed to have a 0 in the denominator. Convenient thing is, for the partial fraction decomposition, we are going to need to factor this thing anyway. Grabbing two numbers that when we add them together, we get positive 3 with a product of negative 4. That'll be plus 4 and minus 1. And according to the factor theorem, that means that we're going to have two domain issues. And those domain issues will be negative 4 and positive 1. Good news is that the given interval is from 2 to 4. 2 to 4 is completely within the domain of this rational function. So we don't need to worry about asymptotes, we don't need to worry about the potential for a domain issue or an improper integral in this case. So rather than evaluating the integral, what we're going to do is head to the partial fraction decomposition. Now that I have a factored denominator, it'll be a little bit easier to figure out. PFD, for partial fraction decomposition, says that after we have factored the denominator completely, which we did in order to find the domain, each factor from the denominator is allowed to get its own rational expression. So we'll set this up as x plus 4 could be a denominator, and x minus 1 could be a denominator as well. Whatever we use for each denominator, the degree of the numerator has to be 1 lower than whatever we just saw in the denominator. Given that both of these denominators are linear, degree 1, we're going to want to see a degree 0 in the top. A degree 0 polynomial is simply a constant. Now, once we have solved for a and b, we have completed our partial fraction decomposition. There are a lot of ways to proceed from here, and some people might tell you different techniques than others. The technique that I think is the most effective is for us to multiply by the lowest common denominator on both sides of this equation. What this should do is cancel out all of the fractions, and we will be left with just a polynomial being equal to a polynomial. On the left-hand side, the two factors that we just multiplied by will cancel out the two factors in the denominator, leaving us with x plus 2. On the right-hand side, when we distribute these two factors to the first fraction, x plus 4 will cancel out, leaving a factor of x minus 1. Similarly, for the second rational expression on the right-hand side, the x minus 1s will cancel out, leaving us with an x plus 4 as the factor multiplied onto the b. Now, once again, at this point, different people will tell you different things. When it comes to having linear factors in the denominator, what I like to do is something called true for all x. I should still be able to plug in any x value and have this expression be true. So we're going to go true for all x. So our goal is to plug something in that can cancel out one of these two factors, or rather zero out the factor so that it's no longer present in the equation. When I see an x minus 1, that indicates to me that one of the things I could do is set x equal to 1. And if I set x equal to 1, this equation would become 1 plus 2 is equal to a times the quantity 1 minus 1 plus b times the quantity 1 plus 4. So with that in place, I can simplify the left-hand side to 3. I can simplify the right-hand side into 5 times b, telling us that b is equal to 3/5. We'll be making use of that in just a moment. Now, that allowed us to solve for b. What I'd like to do is try to solve for a. We should be able to solve for a if we can get the b term to cancel out, meaning that I would like to plug in a value of x that is going to cancel out an x plus 4. The value that I'm looking for, x is equal to -4. If we set x equal to -4, left-hand side would become -4 plus 2. Right-hand side, we would have a times -4 minus 1 plus b times -4 plus 4. Oh man, I hope I squeezed that in there okay. Regardless, we're going to get -2 is equal to a times -5. Dividing both sides by -5 yields that a is equal to 2/5. Now, that completes our partial fraction decomposition and lets us know a couple things back here. So over here on the left side, I'm actually going to evaluate the integral now. So the way that this will work is limits of integration will still be the same. We expressed our partial fraction decomposition as a over x plus 4. Then we calculated a to be 2/5. So I'm going to refer to this as 2/5 over x plus 4 plus, we also said b over x minus 1. We calculated b to be 3/5. So this would be 3/5 over x plus 1. All of this goes inside parentheses, and we throw on the dx at the end. Now, everything that we have up here, that's not right. Hang on, I can fix this. I can fix this! I feel better. Whew. That's close. All right, everything that's up here can be evaluated basically directly, technically with a u substitution. What I'm going to observe is that through properties of definite integrals, I can pull this 2/5 outside and call this 1 over x plus 4 dx. And do the same thing with the second integral and call this 3/5 times the definite integral of 1 over x minus 1 dx. Both of these are technically u substitutions, but because with the u substitution of u equals x plus 4 over here, or u equals x minus 1 over here, in both cases du will be equal to dx. So whatever rule applies to the u will apply to these as well. That is to say, once we integrate, we will get the natural log of the absolute value of whatever was contained within the denominator. So x plus 4 here, 3/5 times the natural log of the absolute value of x minus 1 here. If this were an indefinite integral, we would need a plus c, but because it's definite, we will actually be plugging in our limits of integration. Limits of integration being 4 and 2. Now with that in mind, we need to actually plug these limits in and use the fundamental theorem of calculus to evaluate this area. So I'm going to do that in blue on the top side of the board here. Plugging in our upper limit of 4, we are going to get 2/5 times the natural log of the absolute value of 4 plus 4 plus 3/5 times the natural log of the absolute value of 4 minus 1. Then I'm going to subtract what I get by plugging in our lower limit of integration, which was x equals 2, minus 2/5 natural log, absolute value, 2 plus 4, plus 3/5 times the natural log of the absolute value of 2 minus 1. Of all of the terms that I observe up here, there is one that can be simplified right now, and that is this little guy right here. The natural log of 1 is what this will simplify into. Natural log of 1 can be simplified to 0. The other three natural logs that are up here, outside of using the laws of natural logarithm, like the product property, the quotient property, or the power property, they cannot be simplified further, and I do not intend to simplify them. What I do intend to do to simplify is simplify the arguments. 4 plus 4 would be 8. Absolute value of 8 remains as 8. Plus 3/5 times the natural log of 4 minus 1 is 3. Absolute value requires nothing more. Then minus 2/5 times the natural log of the absolute value of 2 plus 4, which simplifies to 6. In my mind, that would suffice for a final answer. I realize that there are other, again, algebraic properties or algebraic operations that could be done to this to simplify. None of those are going to change the overall value of this. I think it's fine just the way it is. I hope that you found this helpful, insightful, and you all have a wonderful day.